Questo so io. No? Miro? Ah. Voi dovreste vedere qualcosa, ma... Source. Buono. It's like for those at home, I'm tampering with the beamer, with the projector. And from today, from the next Thursday, the lesson will start, the lesson of Thursday will start at 9:15, because we can. Nothing. Funziona sempre meglio, eh? Te levo, te metto. Niente. Vediamo se me li rileva. Displays. No, non ci capisco. Oh, il cavo HDMI non è buono? Nessuno di voi ha un cavo HDMI così? Io lo so, che mi sono preso il cavo HDMI sbagliato. Come si risolve? Tutto alla fine ce li ho qua, ce li ho, cioè lo vedo lui, è lui che non vede me. Soluzione informatica? Ma
lei vede la telecamera o vede il proiettore?
Vede il proiettore. Cioè, il proiettore mi appare come un altro monitor, no? E io vedo, dice c'è un altro monitor attaccato, quindi deve essere lui. E a lui che
non è duplicato, ma invece...
Lo vedo, se lo vedo vuol dire che io gli mando il segnale, lui avrà multipli input e non sa quale input prendere. Prende per costruzione sempre quello sbagliato. Guys, I apologize, but I mean, okay, now you will assist the struggle of the pain of the projectors. If Luca, you are at home, this is because we switched to the HDMI cables. I think. No, niente, non ce ne manco più.
Se no può fare con il schermo su quella casa, noi facciamo quello.
quello. Sì. Sì, però... Sì, poi devo modificare i settaggi di questo, io quello dopo faccio del delirio. No. Niente, eh? No. Lampeggia. So guys, the solution is simple. You open your laptop and no, you niente, because you will see the different things. E quello non lo posso muovere dall'alto da tutti i cavi a 7 mm. Vedi, una volta che non mi so come porta il proiettore, mi serve. Niente. The only solution I see is that for now you look at in the laptop because it doesn't even turn on. Qua forse bisogna fare delle cose. Cioè bisogna... Oh, il cavolo ho cambiato. Mo ci rimetto con l'altro. Quello è il modo, però vorrei, dovrebbe avere un senso il fatto che io vengo a lezione. E poi questo è lo stesso cavo che ho usato nell'altra aula, quindi... Oddio, cavo è sempre, per esperienza. Imputabile. Si fa male, cioè ogni tanto, ecco, mo, qua. Così quello dopo funziona meno. Però vediamo che succede se faccio così. Tanto il proiettore lo siamo giocati.
La seconda a destra dipende.
Questo si muove così, no?
No, sulla barra
no, sulla barretta
Questa.
sulla barretta bianca.
alla destra.
Destra.
Ma
Questo me lo fa spostare.
quella che riguarda.
Altrimenti io non so buono spostare.
La seconda icona da destra.
Questa?
Sì.
Perché non vorrei dire, ma l'ho detto subito.
Yeah. All right. And we say mirror connecting and reconnecting. OBS has failed. The people at home, they don't see anymore. Today's a good day. But this is easy Okay, that was tethering lesson. All right, I mean, I think that people are still, sorry, I apologize for the delay. It didn't depend on me entirely. The projector was not cooperative, so now maybe if I feel like I will cut this, I don't know how many minutes of lesson that we made, but well, and then we will, you will see the video edited accordingly at home, right? Just cut the first X minutes. All right, so go to the slides. Maybe what we can do is also to lower the window there, because there's this fantastic glare. Better. It's more cozy. Today we will see the templates in action. For last time we have seen a way to code the things for performance. I hope you understood that you felt the difference in speed that we could achieve simply by avoiding useless operations, like stack heap allocations of things, copies which are not necessary, and so on and so forth. This was what was happening in the case of dynamic matrix allocation. And we have seen that templates offer us a quite powerful language to do the same things, to achieve the same effect, but with less wasted resources. I have to say that you could have written the same code without templates, only that you would have had to specialize it to a specific size of matrix. Because in the end, what the template mechanism does is to take the source code, expand it according to the template rules, and compile it as if it was a new compilation unit. So each time you instantiate a template, you're just like creating a new piece of C++, let's say, piece of CPP, that then gets digested by the compiler, right? With having the fixed, the constant things in place, and that allow then loop unrolling and all sorts of things. Okay? Today we see something that without the templates, without this mechanism, and without my stress on the operators is not possible. So we will implement a program that exploits the C++ parser, and the parser is that part of the compiler that generates the parse tree of an expression that we have seen already last time. When we were talking about expressions, if you have A plus B, you can see it as a tree where you have plus on top, A on one leaf and B on the other leaf, right? This is happening internally during the compilation phase, right? By playing with the operators, we could attach to these operators whatever function we want. And in theory, you could define, and that's not even hard to do, your type, your basic type that you call symbolic expression. Let it be a string, right? A literal. And then you could define an operator. If I have two expressions and I do expression A plus expression B, let them be polynomials. Then you define the operation that, like what it means to do A plus B. And then you have to produce another type, which is a polynomial, whose values are consistent with the operation A plus B. Do you envision that? That's going to be, okay, we could do something like that. Today we will use this for doing the automatic calculus of the value of the derivatives. Okay? And we will do it in a quite straightforward way. Now, normally I give this lesson to probabilistic robotics. Given that they placed me in robot programming this year, I do it here because it's more meaningful in this context. Okay? It offers you a concrete example on how you can do things very easily, because then using what we write, we are designing libraries, right? Using what we write has to be easy. The implementation is our business. Okay? And efficient. Now, let's talk about derivatives. You all know derivatives, I guess, because you all did analysis 1 or some form of analysis 1. You know what the derivative means. Basically, it's the slope of a function in a certain point. It's the function that expresses the slope of another function at a certain point. This is the most butchery explanation ever. Every mathematician would puke, but I mean, we just like stick to it. In case the function is a multidimensional, we could imagine like a two-dimensional function that you could picture as if it was a surface. We could imagine that the derivative is just the coefficients of the tangent plane in a surface. Okay, the piano, right? That's it. Now, in general, in robotics, you will encounter functions of this form. So a multivariate function f of x, whose domain is a variable x which takes place on a vector space, let's say of dimension m, right? And which produces output on another vector space, let's say y, whose dimension is n, okay? An example of such a function is like when you take a point and you multiply this point by a rotation matrix, right? If you do so, you could see it as f of p that returns you the rotated point. In this case, the function is even linear, which means that its derivative will be constant, right? Anyway, in general, the functions can be arbitrarily complicated. And what happens is that you make mistakes while calculating these derivatives. However, we all know that in analysis, when we were doing the exercises on derivatives, we knew that that was the easy exercise in the sense that we didn't have to understand much. We had just like to do the calculations like a mule, because the derivative is just a set of fixed rules and then you apply them one after the other. If you don't do copy mistakes, you get it. And this looks like a perfect task for a computer, okay? To calculate derivatives. Now, I have also to say that in many cases, while writing our programs, we are not interested in the equation of the derivative. We are interested in the evaluation of the derivative of a function in a point. Okay? Unless you implement a symbolic calculator, which you could do, but it's a different story. Okay? Understood? A symbolic calculator is a program that manipulates expressions, like Mathematica or so, where you can use it for solve your analysis 1 or analysis 2 text exam. Okay? We're just interested in the numerical evaluation. Now, clearly, what is the derivative of, I mean, you might have encountered something like that, I hope so, in analysis 1. What is the derivative of this function with respect to x? Then it's a matrix of functions, where, how big is the matrix? The matrix should be as wide as the input space and as tall as the output space. Okay? So this is the derivative of a generic multivariate function from Rm to Rn is a n times m matrix, where in each component, in the component ij of the matrix, you have to put the derivative of the eth row, in this case 2, with respect to the variable that appears in the corresponding column. So in this case, we will have the derivative of, this is the second row, first column. In this case, in this place, we will have the derivative of f2 with respect to x1. In this case, we will have the derivative of f2 with respect to x2, and so on and so forth. This is the so-called Jacobian matrix that you will also encounter in robotics pretty much. You will encounter two kinds of Jacobians in robotics. You will encounter analytic Jacobian and numeric Jacobian. This is the analytic Jacobian. Okay? All right, but you will encounter. Right now we are interested. Is it all clear when I'm talking of derivative of the Jacobian matrix? I mean, for some of you for which this is obvious, you have also to think that there might be someone that comes from a different background and needs a refresher on that. Now, what do we do in general when we have a complicated function? I hope that some of you in their life sometimes implemented let me see if I have the streaming up. Yes. Huh? Do I have the streaming? Yes, we do. Sorry, but I mean, with one single monitor, you have to take the splitter, but with one single monitor, it's very hard to monitor the people at home. Sometimes you do half a lesson and then you realize that you're off. All right, so going back, normally to calculate the derivative of a function in a numeric way, what we can use is simply to use its definition. We all know that the derivative of a function is the limit for x that goes to 0 of f of x plus delta x minus f of x divided by the delta x for delta x that goes to 0, right? This is the definition of the derivative. Now, what we could do is to calculate this approximation of a generic function, like a monodimensional function, assuming that we have a piece of code that calculates f of x. We could use this very same piece of code to evaluate this thing, this equation over here, by setting a delta x which is incredibly small, like 10 to the minus 20, right? You can evaluate f, the sinus of a certain point, plus 10 to the minus 20, subtract to it the sinus of the certain point, and divide it by 10 to the minus 20. And this is a straight implementation of the derivative, and many programs do that. So whenever they need to have the derivative of a function, they calculate the derivative this way. Okay? This is in case we have a function which is monodimensional. In case we have a function which is multidimensional in general, what we have to do is to calculate the derivative of the function column by column. Now imagine to which piece of code or to which object a function that goes from Rm to Rm corresponds. It's nothing else than, if we want to think it in C++, would be a certain function that takes a vec m and outputs a vec n. Okay, guys? Is that clear? Do you see it? Ah, right. Yeah. No, it's astonishing to have you looking at there during the thing. But are they listening me? And then I realized, oh, that's the monitor over there. This is a failure of projector today, Omar. All right? Understood? Yeah. Should go there. All right. Now, let's see if there are questions. Okay. Someone, Alberto tells me, are we using the central differences method to compute the derivatives? I answer Alberto, no, we compute the derivative, the exact value of the derivative. We will not use the approximation at this lesson. But I mean, I have to tell all the soup in order to reach the meaning. All right. So said, how could we compute the numeric derivative by using this method over a function that goes from Rm to Rn? Well, this function, remember it's just a piece of code in our domain that a real function that takes as input vector in Rm and produces a vector in Rn. Okay, and if you instantiate this function, then so if you call this function, then you get a number or a bunch of numbers, which is a vector in Rn. Okay, clear. Now we can mimic this. What happens when you calculate the function, and the output of this function is going to be a vector, right? You give it a vector as input, xm, and you get a vector as output, xn, right? So now, what happens if I define, instead of defining a perturbation on a single, when I define a perturbation on one single variable of this input vector. Let's say a delta x1, a vector which is made like that. Epsilon with all 0. Epsilon is a small value. This epsilon will be a delta which applies only on the first component, on x1, right? So like you could straightforwardly, in order to calculate the first column, because the first column is the derivative of f with respect to x1, it's going to be, once again, a vector. We could calculate this column just by taking the function f of x plus epsilon, and we could, in theory, we should subtract f of x and divide it by epsilon, but if we want to be more stable, we just like take the epsilon a little bit further and a little bit after the evaluation. A little bit further and before and a little bit after the evaluation point, okay? And this is called the central method, that the central point that your colleague was mentioning. But this is equivalent to this, right? Like if the function is smooth, it more or less returns you the same value. It's only a little bit more stable. But if you want to apply this formula to calculate one of the columns of this matrix, you could easily do it. No, you just like write here epsilon, here you write f of x, and here you instead of dividing by 2 epsilon, you divide by one single epsilon. Okay? Understood? Very good. Yeah, that's the appliances of the lecture hall. Projector fails. He's a maybe future student of me, of the old ones. All right. Numerically, what happens if we think algorithmically to this implementation? It happens that to evaluate one column of the Jacobian matrix, we have to run twice the function f of x. One to calculate f of x plus f of x, and the other time for f of x plus epsilon, and the other time to calculate f of x minus epsilon. Okay? So, in order to calculate the cost of calculating the full matrix will be twice with the central method, will be twice as the cost of twice times m times the cost of evaluating the function once. Okay? Because to calculate this column, you have to evaluate f twice, and you have twice, and you have to repeat this m times. Right? So this method is more stable. Of course, if we would use the other method, we could do the other method means f of x plus epsilon minus f of x, and dividing by epsilon, we could evaluate the function only m times, because this stays fixed, right? So we would gain a little bit of performance, but we would potentially lose a little bit of accuracy. Okay? This happens when you calculate the numerical differentiation. I mean, what is the how to say, the benefit of numerical differentiation is that it's exceptionally easy to calculate. Basically, I hope that you can imagine that writing the code that implements that, it's quite straightforward. You just like have, for each column, you have to take an epsilon, you have to generate a vector where you put an epsilon in the column I, right? Then you have your evaluation point, you take x plus this new thing, you pass it through f, you get the value plus the increment, you subtract it, you get the value minus the increment, and then you divide it by 2. And then this way, this output would provide you the column, okay? And this you could already do it, right? And I think you have all the means to do a static version of the numerical differentiation. If I would have to implement the plate version of this, I would just like write a class that takes a function object that implements the function. And then by having this function object, I can do the repeated invocation and have a static piece of code that calculates the numeric derivative of this object that I pass as a function object. The downside that we encountered quite often with the numerical differentiation is that the step that looks trivial is not. It's typically the choice of the epsilon. So how to choose this epsilon, right? We all know that it should be small enough. But if we take a too small epsilon, remember that we have computers that work with fixed precision. And then what happens is that basically we incur in issues with the digits of the machine if the epsilon is too small. If the epsilon is too large, okay, we might not have issues with the machine, but we might have a too large derivative because the limit of the incremental ratio is not yet converged, still with a big delta. And so we have a poor approximation of the derivative. My suggestion is that and the other, how to choose epsilon also depends on what I call the bandwidth of the function, how rapidly it varies. If I have a function which is very smooth, I can relay, which means that changes mildly, whose derivative is rather small. I'm fine in choosing reasonably large epsilon. If the function is very irregular, well, if I choose a too large epsilon, I might jump out like of relevant parts of the function, right? Is that clear? Anyway, if you want to check your hand-computed derivatives and plot them on the screen, you could easily run this automatic numerical differentiation and check that the plot of the derivative that you computed by hand is similar to the plot returned by the numerical differentiation. Okay? And now we come to the meat of today. Now, and I hope it is also clear that the numerical differentiation provides us an approximation of the true value of the derivative in a point. It doesn't provide us the value of the derivative in the point, because epsilon is not zero. Okay? Question is like, can we think about a process or look at the derivation process and get some insight that allow us to use the peculiarities of C++ to make the machine calculating the derivatives, the function or the value of the derivatives exact up to numeric precision, which is different from the numeric precision of the numeric Jacobian, because there we inject noise with the epsilon. Okay? And the answer is, of course, yes. Now, to see the templates in action, I would recommend you to consider the parsing tree. So to consider this data structure that the computer estimates while parsing an expression, while generating code. I think we have encountered already the parsing tree when I was mentioning the expression in C++, so it should not be a terrible thing to observe that this function over here has this one parsing tree. So the last operation executed is the division between the left-hand side and right-hand side, so it's the root of the tree, and then on the left-hand side we have a cosinus on the one end, and on the other side we have a sinus. Then the cosinus is run on an argument which is the product between 5 and x, and on the other hand we have the sinus that is run on an argument that is the exponent that is run on an argument that is the plus between x and 3. Okay? But we don't have to evaluate the code. I mean, it's a very educational exercise to write a recursive descent parser, so a piece of program that generates this tree from the expression, but I will keep it for myself. What we will do is to use this mechanism, and you already start sensing that what we will be doing is to overload the operators and the functions of C++ to work with a different type that will contain the derivative. Do you see the mechanism, the machinery? All right, now let's think about something Sure. Well, I mean, was coming from analysis 1. The famous chain rule, which is different from the chain rule of probabilities, but it's another chain rule in probabilities. Do you remember that to evaluate the value of the value? Remember that we are interested in evaluating the value. We're not interested in evaluating, not yet. We're not interested in evaluating the function, the expression, right? We're interested in evaluating how much is the derivative of this function, f prime of x, in a certain point. So if I give you a function f of g of x, and I ask you, how much is the derivative in a certain point that I call x with this minimum, this hat, x breve. Do you see this little thingy over here? You from there? So this is very important. I'm interested in evaluating the value in that point. Okay? But to calculate it, to calculate this value, we need to know, first of all, the formula, so of the derivative of the outer function of f, right? Because we need to, the derivative of f of g of x is f prime of g of x times g prime of x. This is the chain. Like, to carry on this evaluation, we need to know the formula of the derivative of f, the formula of the derivative of this object. So if this is sinus of cosinus of x, we need to know the derivative, that the derivative of sinus is cosinus. Okay? Do you have it clear, guys? So this is the first ingredient that we need to know. So we need to, when I say the formula, this means that we need to have a machinery that is able to evaluate the derivative of the outer function in any arbitrary point that we want. Okay? So, for instance, having its expression. All right. Then, first ingredient. The second ingredient, we need to have access to the value to this value y, because in order to calculate f prime of y, we need to know how much y is, right? And then the question is like, what do I need to know to calculate this? Well, we need to know to be able to calculate g, but not g in any random point. We need to be able to calculate g in the linearization point, in x breve. Okay, not everywhere. What we're trying to do is to restrict the requirements. We don't want to have things or impose the user to define stuff that we are not going to use. Is it clear that for the outer thing, we need to be able to calculate the formula, because we don't know how much y is going to be in this stage. We need to be able to calculate the value of the argument of f. Let's call this value y. So we need to be able to calculate the projection through g of x breve, which is the evaluation of g in x hat. Agreed? Okay? And the last thing, and let's call this value y. Okay? And the final element that we need to have, and this is the strong point, we need to have g prime, the value of g prime of x linearized. We don't need to have the expression of g prime. We need to have the value of g prime. Okay, guys? And let's call this value of g prime y prime. Okay?
Excuse me, Professor. This means that when we do the incremental ratio, we use, instead of x, we use x at?
No, we don't do the incremental ratio.
Okay.
No, we're just like laying down what, say, your colleague says. Excuse me, this means that when doing the incremental ratio, we can use y prime instead of... not really with this machinery. Like, what I would like you to feel is like that these are, if I have these ingredients, these ingredients, which is the formula of the derivative of f, the value of the argument of f, and the value of the derivative in the argument, then in the end I'm able to calculate f prime of y times y prime.
Is this just an analytics speech?
It's an analytic speech. I'm not talking about programming. I'm just talking about the phenomena. But sometimes, like when you want to implement things, you have to look at the reality and then you implement it. All right? Okay. I'm not talking about programming yet. Clear, guys? Let me see if at home I have complaints. No. Was good. All right. Oh. It's not cooperative, this button. All right. Then, this is all we need, right? I mean, just hammer it in your brain, right? We don't need anything else to calculate the value of a generic derivative of a function in that shape. Then the question is like, how can we instrument the parsing tree of C++ to calculate the value of a function and the value of the derivative of a function? Okay? We want to carry on both. Why do we need to calculate? We are interested in the derivative. Why do we have to calculate also the value of the function if we are interested in the derivative? Well, we need to carry on also the evaluation of the value of the function, because according to this rule, I will need to be able to have access to y, which is equal to g of x. So I need to carry on in my parsing evaluation also the value of the of the derivative in a subtree of my parsing tree. So I need two things, right? Now, so if I have to construct an evaluation mechanism for this new, let's say, algebra that I invented, these new elements, each element of my parsing tree will have to store the value of the function, y, and the value of the derivative of the function, y prime, the value. If I have this, then how the word would look like, right? Let's see. So every element, every value in my tree, so both the leaves, the constants, the variable, and whatever, before it was a float, let's say, now it's a struct composed of two fields. The first two floats. The first float is the value of the function itself, and the second float is the value of the derivative, whatever it is. Okay? It's another float. Is that clear? Now, let's think about how could we design this mechanism. The new data type on which this system works is then a pair of things. Is that clear in class? Yes, no? I want to have feedback. Feedback me? You can also say no, because if you say no, probably you're helping someone at all. If you say no. Huh? It's not clear to you. I like it. Thank you. Okay, a colleague of yours says, which is a representative of many, only that he has the pride to speak, says that this is not clear. I mean, then I start from this slide. The slide is perfectly clear, he says. All right, now, imagine that I want to calculate the value of this expression over here, right? Then what do like from a point of view of data structures, right? What do I need to possess? I need to have access to y, right? So, and to what exactly I need to have access in terms of y? I need to have access to have access to the value of y. Now, if you think in C++, the value of y is the result of the evaluation of a parsing tree, right? Like on top is an element that the root of a subparsing tree, and it's the value of the subparsing tree, right? What is y prime if you think about it in C++? Is again the evaluation of the value of a parsing tree, only that this has to be the derivative. Okay? So if during the evaluation process, I bring up two values, two elements. One element which is the value of the parsing tree, and the other element which is the value of the derivative of the parsing tree. Right? And then having access to the formula of the derivative of f, because I have access to the formula of the derivative of s, right? I could calculate another pair of values. And this pair of values will be the value of the derivative of this object over here in the point that I calculate by taking the y. So I take it from the bottom part. I pass it through my machinery that calculates, evaluates the expression of f prime of y. So I have a number. And then I take this number, I multiply it with what I have from the bottom concerning the derivative, and I have the derivative part that I'm ready to propagate up. And then I do the same with the value of the function, so like with f, right? Because I need to propagate up a pair which consists in the value of the function in the point and the value of the derivative of the function in the point. Is that more clear now? So for this reason, if we would have a pair, no? We define a new data structure that it represents our scalar values. Before it was float, now instead of being float, now it's an object consisting of two fields. Right, guys? And these two fields are two, let's say, floats, in this case. One that stores the derivative and one that stores the value of the function. Do you have it clear? Now, just think about, I want to implement this method. So I substitute, I do not have any more float. Now I do have this pair. Clear? And what I'm telling you is just rewrite the implementation of the different functions in a way that they are consistent with this definition. Now, if what is the derivative of x, of the variable x, right? What is the derivative of the function with the derivative of the function x? No? F of x equals x with respect to x. It's 1, right? So, if I want to have a variable used in differentiation, I could just like have a pair x, where x is the value of x, because we're interested in calculating it in the point, and 1 in the second part, because 1 is the derivative of x of the function x with respect to x. All right? What is the derivative? The derivative of the function constant of the function f of x equals a with respect to x? 0. No? It's flat. Right? So, and generalizing, a constant become a pair, constant 0. Do you get it? Very good. Now, let's say I want to implement the function sinus. Sinus that operates on this dual value. What sinus has to do? Well, the sinus takes as input, because it has to produce a thing. I call these elements dual values, okay? These objects. That takes as input a dual value, all right, guys? And produces another dual value. The dual value in output will require to have the first element equal to the sinus calculated on the input, on the value of the input function, and the value of the second element will have to be the derivative of the sinus with respect multiplied by the derivative of the argument. Okay, look at this function over here. If I want to evaluate the value of sinus of u, well, I find here sinus of u. Okay, guys? If I want to evaluate the derivative of the sinus of u, but u might not be just a constant thing, it's not an x. is a generic expression which is attached to its value of derivative. Let's call it u prime. So the derivative of this object by using the chain rule is going to be the derivative of the sinus. So I find here cosinus of u is the derivative of the evaluation of the derivative of the outer function, so sinus becomes cosinus, in the evaluation point which is u. No? This would be f prime of y evaluated in y. No? Do you see it? So this is f. This is f. This is the derivative. So it's f prime of y, so u, evaluated in u, because u is the argument. Okay? And then you multiply to the right by the f prime, so by g prime of x, which is equal to y prime, which is your u prime. Do you see it? Do you see that this thing over here is exactly what I've implemented here? Just like do a matching. What is y prime? Is u prime. I could call it u. I could call it y. If I would call it y, probably you would understand it better. And that's what I'm going to do. Sin of y. Or I will change it later because now I applied some rewriting rules to show you that now do you see that this implementation here follows, it's just the transcription of what I've written in the previous slide, only that instead of putting a generic f, I restricted f to be the cosinus, because I'm implementing the piece that calculates the derivative of the cosinus. Okay, guys? Is that clear? And then if I apply the very same on the bottom, then you maybe I could do this. I could just like put, could put it, okay. Just I don't want to have, you know, u prime otherwise I mess up with the slides. Okay, guys? Is that clear? Now, being clear the first line, it should also be clear the second line, and also the third line. Right? Okay? Right, now these are, we managed to handle the atoms, which is basically the constants and the variables. Clearly, if a variable is not used for this differentiation, this variable will have the value of the derivative, so to set to 0, because it will become a constant. Okay? All right. And then let's do the binary functions. Does it sound familiar? So, what is the derivative of the sum? I have two objects, two dual values, right? I have u primes and v primes. What is the value of the value of the sum of these two? Well, will be for the value part will be the sum of the values, and for the derivative part will be the sum of the derivatives. Do you agree with me? Okay. What is the minus? Same, only that I replace the plus with the minus. Agreed? What is the product? Well, the derivative of the product of two things, two functions, or two dual values is for the value, so for the value part is just the product. I take u and v and I multiply them. Once I want to do to evaluate the derivative of the product, if just think to those as if they were two functions, I have f primes times 3 plus v primes times u. Okay? Does it sound consistent with what you know? And the last one, if I have the ratio between two dual values, what I will have is just go back and implement like if you have f of x over g of x. No? Clear? But do you understand that now we can rewrite the operators that do exactly the same thing? And that's what we're gonna do. So mechanically, we can implement this entire mechanism in in 200 lines if we want to cover all possible operators and things, but it requires even much less of code. All we need to do is to define a type which we will call dual value, which contains both a value and its derivative. And of course, we have to redefine all operators and the standard math functions. Okay? And so like here, there is the link out, the thing, 03 Autodiff, which imposes me to go to the source business. And you know the ritual of zooming. The default font. Now, sans. No. Why? Which font do you like, yes? Guys? Ubuntu? Bravi. Bold. Yeah, maybe larger, eh? Function. Set default font. Nice. Fat. Now, there's one thing that I have to say. If I start filling the system with the overloading, I managed to get the compiler crazy. Therefore, I had to basically take you know that when you call sinus, you don't call sinus. You call a function which is called sinus of float if it's a float, or sinus of double if it's a double. Sinf or sind. Okay? Now, in order to help the compiler not to get crazy, I just like I included the C library of math, and I rewrote basically stupidly the function so that it doesn't mess up, because C doesn't have overloading. C attempts the cast. C++ tries to match, to adhere a little bit to the overloading rules. So what I had to do is to say, okay, I define a function that I call sinus that takes a float and gives a float, and then calls the sinf function of the math library. Okay? This is something I had to do to help the compiler digesting the business. So I did the same with every other function that you find in the pool, right? In the C library. Do you understand that? This is not part of the lesson. I had to do it to avoid the system blasting. Anyway, here we go. Of course, we are in templates, and then I might, maybe in the future, I also envision the possibility of calculating derivatives on fields that are complex, right? So or maybe I want to have code that works with floating point precision or with double precision for floating point, right? So it might make sense that I just like define the dual value, which I call dual value underscore, over a type T that could become either float or double. Okay, guys? And just for me. And then I specialize it. Depending on whether I want, for instance, if I want to compile code on certain versions of CUDA, I can't use doubles. So I need to use float. And so in this case, instead of rewriting everything, I just like say, hey, use the float here. Okay, guys? All right. Okay. Interesting, I have two elements, one which I call value and the other one which I call derivative. I could also do more. Let me do one thing. I do a query replace for you on the spot. Call it scalar type. Makes more sense. All right. Now, the constructor of a dual value. The constructor, let's make a constructor that just assigns to both the value and the derivative 0. Someone would ask me, this is a magic thing, we will see it later. It's basically finding the cast operator. When you want to take a dual value and you do dual value equals 5, this means if I want to see this object, I can assign this object, no. If you do float f equals a certain dual value, this will apply to the dual value the implicit cast. This overrules the cast, but I don't want to talk about it in this moment. The constructor, you want to see it as initializer list, we see it as initializer list. Just for consistency. This is all code, and then I just like, I evolved over time. Okay? Or this other, you could use again the initializer list, but yeah. What is this constructor doing? Asking in the class. No? Look at the, let's call it scalar. It's not copying. Yeah, if I want to create a constant, no, I can just write dual value of 5. This is a constructor that matches. The argument list is just a scalar, so it's just one number. Okay, so I could just instantiate it by saying dual value of 5, and then I have an object that represents a constant in my domain. Okay, it's overloading the constructor. Right? Okay. Then clearly we could have an initializer with 2 arguments. So here I'm overloading all constructors for sugar, so to say. Okay. Fine. Operator equals, right? This is an operator equals of dual values that has or that matches if I do dual value dv equals 5.7. This is an assignment operator that supports the assignment of a constant to a dual value. Do you see it? Of course, here we are seeing the full sugar. It's not a minimal example, because then at least you have something that you can use. So it's all little nitty-gritty of C++. So in this way, I'm also supporting dv equals 5, right, in my language.
Sorry, I don't understand. Why do you return anything in this method?
I return this.
If you assign, why do you return? I don't understand.
Oh, because I could write expressions like a equals plus equals b equals 5. So if I do this, then I need to return a value. If I don't return anything, it's not a sin. It will go through, but I will lose the possibility of writing such expressions. Which I don't know why one should do it, but just be consistent with the syntax of the rest. Okay, plus equals. Do you have questions on plus equals? Operator plus equals returns, calculates, the value is the sum of the values, the derivative is the sum of the derivatives. Understood? Fine? Minus equals? If you understood the plus equals. Star equal. It's like when you do the multiplication in place. Well, the value will be my value multiplied by the value of my friend. The derivative will be my derivative multiplied by the value of the other argument plus the my value multiplied by the derivative of the other argument. No? It's a one-to-one implementation of what we have seen in the slide, right? Divided equals, no? Shall I continue or it becomes boring? Let's see, greater, right? Operator greater. Operator greater equals, I just wanted to re-implement these things to have an interface which is consistent with the classical things that we normally do with numbers. So if you use these dual values, then you can also forget about them and use them as floats. Okay, guys? Minus equals. This is, well, to print the values. And then we start having the functions. Here we see a bunch of template functions. Template functions that, you want to, first let me show you the sinus, the cosinus, the logarithm, the sinus. The sinus clearly is not a member of the dual value. In the case, if I want to implement to support the sinus in my language, I need to write a new function which is external to the class, because when I call sinus of A, I don't do A.sinus. I call sinus of A, right? So I need to define a function, which is, in this case, a template function. Why a template function? Because I introduced into the dual values the potential scalar. Okay, guys? The fact that I could have the dual values which could be instantiated on float, on double, or other things that I might invent in the future. So I need to write a template function. So that operates on, that was free argument is t, which is the template inside, produces a dual value of type t, takes as input a constant reference to a dual value, which is the expression evaluated in the sinus, and then the implementation will be simply return dual value of t, because remember that when you create objects, you have to call the template fully. So it calls explicitly the constructor, passing as value the argument op value, and passing as derivative the value cosinus of the argument times the derivative of the argument. Okay? I mean, this is a non-standard. I mean, don't get scared. This is a non-standard course of C++. We are really going skyrocketing here, right? But it will last 2 more lessons, and then we will do the nullity, basically. Everything will be, else will become a slope. And then in the end, it's to your value, I think. Right? Same, the arc cosinus. These are all the classical derivatives, right, that you find in the analysis book. Okay? Of course, if you want to implement, there are other operators, I think, that I had to define outside of the class. Yes? Well, that's more or less it. Then at the end we have a fantastic, oh yeah, here you, well, convert, this is bullshit. Then we have 2 usings, because we want to forget the fact that we use template. We have dual value f and dual value d, that we just close the template on the spot. Okay. Once we use this mechanism, let's see how it looks like. Okay. Let's we want to construct a function that calculates the derivative of the function. I think I had it in the slides. No, I don't have it in the slides, but I will write it here. Okay, The function is cosinus of 5 times x divided by sinus of x plus 3. This is the function that I want to represent. And I want to enable my autodiff mechanism. Okay? So I call this function, I would like to write a machinery, right? A thing that I call f, that I pass a float value, and then if I set this boolean to false, it doesn't compute the derivative, it just returns me the value of the function. And if I set this value to true, it calculates me the derivative. Okay? So, false, so if it's false, returns the value. This is how I remember things. If it's true, it returns the derivative. Okay, guys? Now, I need to create, remember that we need to operate with dual values, so I need to create the constants. I create the first constant. Let's say it's a dual value of float. Remember, why dual value f? Because I had the using the other 5. And I call it underscore 5. And it's a dual value of 5. I have another constant that I call underscore 3, and I call it dual value of 3. It's static and it's constant, because it's a real constant, right? And declaring static inside a function makes this variable persisting between function invocations. But given it's a constant, I don't care at all. Just like put it here. I could put it global, but it would suck. This way I just like put it locally there. I see it only there. Okay? And then I need to calculate. I want to construct the dual value for the variable under which I carry on the evaluation, right? And I call it, I use the symmetric syntax, I call it underscore x, and in this way I'm gonna call one of the constructors that we have seen. Which constructor am I calling? I'm calling the constructor with the t, with the scalar type inside. Okay? And automatically the derivative is 0, because if you remember the constructor, if the derivative was unassigned, then it was 0. Okay, then yeah, if value false derivative true, so it's 0. If the value is true, then x dot derivative is equal to 1, because we want to compute the derivative, we have to put in x the derivative of x. In the function, in the value of x, the derivative of the value x, which is a function, is 1, the value of the derivative. And so like, we will have to say x dot derivative, so this variable over here, we set the field to derivative to 1. Do you see it? Okay. Then this is the black magic. We call these are all our operators being called here, because everything matches the overloading that we have done with Autodiff. These are all dual values that we are passing in. So which functions will be called are those that we have declared in the other 5. And of course, the result of this machinery will be a dual value, right? Do you see it? Or, all right. And then we have this complicated statement. If value false derivative true, so if value, then, so if this is true, this means that you have to return the derivative. If this is false, then this means that you have to return the value. If you want to change this business, all you have to do is just to change this function over here. Remember that we didn't, now I'm responding to all those that said increments. There's no increments here, right? We're using the analytic expression to evaluate the derivatives. And then to calculating x, y, dy over dx, the value of f in x is, right? Let's see if it compiles after all my massaging. Just rude. Oh, grazie. Thanks, compiler. This is the safest thing. In the old versions, you could override your source code. You're very happy, okay? U equals 0. What did I do wrong? If you use the initializer list, you have to use the initializer list. Yeah, another one. Yes. If you use the initializer list, it expects a business like that. Maybe if I change C++ standard, it will digest also this, but all right, add the test. That's it. I mean, you might not realize the power of this machinery, or you might realize it. But imagine that now, whatever function, it doesn't matter how complicated the function is going to be, we're going to have the exact value of the derivative whenever we want, evaluated analytically. Okay? There are no approximations in the game. And using this mechanism of the templates. I mean, this is, of course, we're going to a little bit to the extreme. This Autodiff lesson is like to show you that you can interact with the language itself and change the semantics of how the language, the expressions are interpreted, right? Now, the exercises on this lesson is one, and it's very compact. I mean, for the first time, we will not provide any stub. So, because I want you to start writing from a blank piece of paper, we will just create a folder and we will do everything from scratch. So, there are two files, and one, ad.h. You have to take it, copy it somewhere, write the CMake lists, copying from somewhere else. I'd like you to bootstrap yourself, right? And we will bootstrap ourselves all together at the correction of the exercise. All I ask is this. I'd like you to calculate a program that computes the values and the derivatives of a function. This is a function that goes from R2 to R1. Okay? In the range, so it's 100 values basically, because no, more. It's 20 times 20, 400 values. So this function is defined in the range -1, -1, 1 for x and y, right? And then I'd like you to evaluate all the values with a step size of 0.1, which means 400 values, okay? And for each point, it evaluates the value of the function, the derivative of the function with respect to x in that point, and the derivative of the function with respect to y in that point. I give you two hints. When I derive, have you seen how to toggle the derivation with respect to a variable? You just set derivative to 1 or to 0. So you just like write this block, you take two arguments, and if you're deriving with respect to x, you set the derivative of x to 1 and the derivative of y to 0. If you're deriving with respect to y, you do the opposite. No. Because once you derive with respect to derive a function with respect to a variable, the other variables become constant. Okay? It's a snippet thing, but and remember that you could also write matrices with dual values, huh? Because the language will support it. Remember that we have the scalar field in the matrix in the math class, and it works. Just right. You don't have to think anymore. You let the language go. Now that's the exercise. I think. Are you fit? Do you have questions? Let me check the remotes.
I have two questions.
Yes, excellent.
One of directed properties, but it should not be in the first line and second line inverted. Y on derivative equals to 0 and x dot derivative equals to 0. Because if y
yes, your colleague is right. Yeah. You know that copy paste is the mother of all evils. Yes. Yeah, your colleague spotted the point that there was a mistake in the slide. I mean, guys, there will be mistakes in the slides. It's the first year, so you are Guinea pigs.
The other question was about the Boolean arguments. I didn't understand actually what it does, why we need to use it.
We don't need to use it. It was like only to, like, you mean in practice. Your colleague asks the dual value. Here, this Boolean value. So,
Exactly.
fine. I mean, this function takes, this thing takes a number, a point, an evaluation point, and returns me a single float, right? So, if I want, this single float might be two things, might be the value of the function, or might be the derivative. And this selects whether I want the derivative of the, or the,
So if I call this function, I could say if I want to receive the value of the function,
or the value of the derivative, exactly.
Okay.
So,
Okay, it's not fundamental actually, if I want to use it.
you know what I mean. Yes.
And also about the exercise, so we have to actually return meridian.
You will put you will return you will do the following. You will put a selector, or you can either you put a selector or just like return a bunch of dual values. Okay, I put a set just like to see, because I'd also like to plot it. Imagine that you write it in the file and you can see what's going on. I'd like to see I would do, if it's an enum, if 0, then return the value. If 1, then return the x, and if 2, return the dy. Then I will have three matrices, right? 3 400 by 400 values of this function that then I might want to plot it. Understood? Clear? Or you could also do everything and print it in a tabular fashion. And then there is a fantastic program that is called GNUplot that allows you to plot what's going on. So you just write it in a text file separated by spaces, or write it. You write it. You don't know how to write the things in a text file yet, but you know how to write on standard output, right? With the C out, you can write, right? So you can simply redirect the things. If you want to cut the output of a program to a file, for instance, you could do this. Basically, with the greater operator, you take anything a program writes and you flush it to a file in the shell. No questions from home? I mean, I would also close the lesson here. I mean, let's say, I'd rather prefer to do, I'm overloading with credits, right? I might teach more than 30 frontal hours, but then I'd rather prefer to have the lessons shorter, that you can breath in between and then you can do the stuff. So even if we do only 1 hour today, there's no seppuku for anyone. I'd let you experience the things. So, if there are questions, I hope that people will say something. And and that's it. Bye. I send you in peace, my sons.